Hello, everyone. My name is Cheng Li. Today, I will present our recent work in which that we built an automatic tool to select the right consistent levels for replicated systems. It's a joint work with my colleagues, Alan Victor from MPI SWS, João Nuno, and my advisor, Rodrigo, from Nova University of Lisbon. I would like to start my talk to showing you the work we have done 2 years ago. In that work, we proposed RedBlue consistency. It's a consistent model which we can resolve the tension between consistent semantics and performance when we build a replicated system. The basic idea has two aspects. The first one is we really want the system to be fast. In this case, we define a type of operation. We define a type of operation. It's a blue operation. It can be always executed locally without contacting with any other replicas. Because of this property, they can be very fast. But it only give you the weak consistency semantics. On the other hand, we also want the system behavior always correctly. In this case, we would like to ensure all the replicas to reach the converge to the final state. And also, we want to ensure that the application-specific invariants can be violated during the execution. To achieve this, we identified that the blue operation is not enough. We should specify another type of operation that always need coordination to be executed. We specify this part as a red operation. Because of this global coordination, this type of operations can be very slow, but give you strong consistency guarantee. The whole framework of the RedBlue consistency is try to strike the balance between this weak and the strong part. The key question we would like to ask, what's the principle to partition? So we additionally provided this principle. How this works, for every operation, we first check whether this operation commute with all the other operations, including itself. If not, we must label it as strongly consistent. In this case, we can ensure state convergence. Otherwise, we continue to check whether it has potential to violate the invariants or not. If so, again, we label it as strongly consistent to ensure invariant preservation. At the end, only the operations that both commutative and invariant preserving can be labeled as weakly consistent. In our context, it's blue. Pay more attention that the good performance doesn't rely on the partition. We realize that it highly depends on how many blue operations you can have in the system. Right? But in the fact, we realize that not many operations can be classified as weakly consistent. So I will motivate this by example. Suppose we have the banking example that uses the consistent model, and we have the shared bank account has initial balance $10. At the very beginning, we want to make a system really fast, so everything weakly consistent. We will be able to process the deposit and the accrued interest simultaneously at 2 replicas. And finally, we replicate the operation remotely. This gives us a divergent state. This divergence is actually because of the fact that these 2 operations, they don't commute. That's really hurt the performance. To solve the problem, you basically have 2 solutions. The first one, you try to pay the cost for the coordination. Another one is you find a cheaper solution to resolve these conflicts. Therefore, we propose a concept of a shared operation which allow you to maximize the weakly consistency. Sorry, that doesn't work very well. Okay, so in this case, instead we start with exactly setting. Instead of propagating the operation, we create a shared operation that encodes the side effects in the commutative fashion. For instance, in this case, we translate multiplication in the accrued interest as the addition. Therefore, after the replication, we get the convergent state. Cool. Reach this part, I just briefly go over the framework we did before. And based on the previous the experience, we identified that we need to manually do this thing, hold things. And this manual work is non-trivial and also can be error-prone. So therefore, we would like to have a tool which automates this adaptation. So this is where the SIEVE comes from. we built a tool which automatically transform when the operations go into the system, we execute the system. Alongside the execution, we translate the side effects of the operation into a commutative shadow operation, and then we check the invariant preservation property over these operations, classify them into two different categories, the weak part and the strong part. So this talk, I will basically focus on these two aspects. And next, let's first focus on how we actually generate this kind of shadow operations. While we considering this task, we identify a few challenges. The first challenge we identify is that we want to target a large class of applications in which programmers can implement the operations that manipulate the state in arbitrary way. Therefore, we would like to find a standard solution to make these arbitrary side effects commute. Second, we also would like to reduce the input we require from the programmer side as much as possible. Keep these two goals in our mind. We first starting to look at applications, like a shopping cart example, e-commercial website, and so on and so forth. What we identify that most applications fall into these two-tier models, where you have a bunch of servers, application servers replicate the Java logic and interact with database. Although the application logic could be complex, we identify that the side effects manipulation are always going through the execution of a sequence of database statements. So in this case, it will give us the chance that we could use this narrow and well-defined interface exposed by database. The basic idea is that we could take advantage of a recent proposed technique in our community. This is called CRDTs, which stands for commutative replicated data types. Briefly, it refers to a list of data types whose operation commute. So in this case, if we can successfully model the database using this kind of data types, then we can easily translate the operation going to the database into this commuting operation supported by these CRDTs. Okay, to leverage a CRDT, you basically, we need to answer the question to find the appropriate mapping from the data types defined in the database part to the CRDT types. We identify two levels of the mappings. The first one is the database table. We map the table to set, and at the fine-grained level, we map the database field to the counter, either a counter or the register where the value can be overwritten. So with this mapping, what we did there is we can automatically, at runtime, analyze this SQL statement is being executed and figure out what kind of side effects you want to apply there. In this case, we could transform each statement into one or multiple CRDT operations. Remember that each operation could consist of a sequence of SQL statements. Therefore, finally, the generated shadow operation also could consist of the sequence of a CRDT operation. The one actually shown on the slides is the one such example for the shadow operation at a very conceptual level. This transformation process only requires the programmers to place the CRDT tag in front of their table definition or field definition to specify what kind of merging semantics they want to use to handle concurrent updates. To illustrate how this works, I would like to show one example. Suppose we have this banking table definition here. Each record will have three attributes: ID, name, and also balance. The text in green color represents one possible annotation for this particular example. I will not cover details. With this annotation in place, it's very easy for us to intercept the calls going to the database and to create the corresponding CRDT operations. Let's take the last one, LWW, as an example. That stands for last right win strategy. This specifies if you have if you have a set of concurrent updates for a particular field, you always can deterministically select one to determine the final value. So if you have this statement to modify this kind of field, it's very easy to translate the original statement into a CRDT operation where we associate the timestamp with the record you want to modify and only overwrite this value if this timestamp is higher than the current one stored in the database. I spent the first part of my talk so far just covered the first part, how actually we could encode the side effects into a shared operation that commutes. Next remaining question is how actually you can decide what kind of consistent level you want to try. To do this, to accomplish this goal, we identified that there are challenges that we would like to do this accurately, and also at runtime we want to impose just little overhead. Before I lay out the final design choices, I would like to show you the strawman solution I come up. In this strawman solution, we first analyzed to go over how the operation is going be executed. So once we have the operation, it only be triggered at runtime if you receive the user request that associated with a list of parameters, and then these operations will be executed against the initial state. This particular combination will determine what kind of shared operation you will be generated at the end. In order to enable a very efficient runtime checking, we would like to ask the following questions. Actually, can we statically determine what kind of such combination of the parameters and the initial state could produce a weakly consistent or a strongly consistent shared operation? If we could do that, then the runtime checking is very efficient. So to do this, we take advantage of weakest precondition analysis. That is the popular technique people are using in the programming language community. Basically, the idea is that statically for this original operation, we identify a weakest precondition for that one, which summarized all the possible combinations of the parameters and the initial state, which could produce an invariant preserving shared operation. And to the runtime, this checking would be very simple. You just go there and to fetch the corresponding weakest precondition, you follow, and then to evaluate the true or false value for this weakest precondition, the outcome will determine the consistent levels. I will detail later on. However, this solution could be conservative. The conservative means that we get a lot of operations that they are strongly consistent. The fact is that this static analysis could be very expensive. Let's consider an example that you want to maintain that the global variable x never go below 0, and you have operation foo actually manipulate x in different ways. So we found that if you compute the weakest precondition for that one is really expensive and infeasible because it requires us to go back and forth to invent this hash function. So the classification will be conservative because to make the system at the safe side, we would like to generate a false condition for that one. Therefore, the false condition implies that all the shared operations generated will be labeled as strongly consistent. However, we found that even this path condition is very complex, but the side effects are very simple for this operation. There are only 3 patterns of the side effects. For example, if the 2 if conditions are true, then you minus 10 from x. And if the second if condition fail, then you do nothing. And at the end, if the else condition is enabled, and you add 10 to x. Obviously, except the first pass, the other 2 passes never drive x below 0. Therefore, if we shift our focus from the original operation to the side effects part, it gives us more chance to class operations as weakly consistent. Let's see how it works. So in order to do this analysis over side effects, the first question we would like to ask is how to identify all the possible side effects. So in this case, we incorporate a path basis analysis In this case, for every control flow path in the original operation, we create a template which summarizes all the possible shared operations that can be generated along that path. For example, if we take a look at the previous example again, the things pointed by the arrow are the templates for each path. And finally, this weak precondition is done over the parameters of the sequence of CRDTs that we encoded in the template. The outcome is much, much better because you see we only get the fourth weakest precondition for the path actually try to -10 from x, and for the rest of the two are okay. So we're happy with this less conservative classification. All these design choices finally constitute this architect of our SIEVE, the tool. Basically, we have the mix of the static analysis and the runtime checker. The high-level idea behind that one is we want to do a lot of work offline and just do a little work at runtime. So we require the programmer to specify the CRDT annotations I described before and to infer a set of application-specific invariants. After that, the static part actually taking these two as input, produced a table. In that table contains all the possible templates and also the corresponding weakest precondition. At runtime, we run the SIEVE with application, and it will intercept the database calls and generate the shared operation. And finally, it will go to the table and retrieve the corresponding condition and do the runtime checking. The true value implies that we can accept the weak consistency semantics. Otherwise, you must be coordinate for strong consistency semantics. Okay, in the first 2/3 of my talk, I basically talking about how actually we design the SIEVE and implement it. Later, in the rest of my talk, I would like to cover how actually we construct the evaluation part to demonstrate SIEVE. We have a bunch of questions here, but don't be scared by this question list. I don't have time to cover all of them, just give you the idea that we evaluate the experience, we adapt the SIEVE to use to the applications, and also we evaluate how good the performance of the static part and the runtime part. Due to the time limit, I only cover how the runtime overhead looks like. In order to investigate how much runtime overhead our tool introduced, we deployed two applications, namely TPCW and Rubies, in 3 different configurations. First one, we just run original code interacting with the MySQL database. And second one, we manually adapt these two applications to RedBlue consistent model to use that framework we built before. We call this menu. These two actually are serving as baselines. And last piece is that we run the two applications with SIEVE. That work, everything is done automatically. We compare the throughput and latency across these 3 configurations. And these 2 curves represent TPCW and Rubies respectively. And in these 2 graphs, the blue curves, also the bottom curves, represent the original code. That is achieve the best performance. And 2 other curves represent either the manual adaptation and the SIEVE. What we can conclude here is that SIEVE achieved almost the same performance as the manual work does. So in this case, we didn't introduce much overhead at runtime. And we further investigate, because just remember that we need to do the runtime labeling. In the case that we need to fetch the condition to evaluate, use the runtime value. Therefore, we further investigate how much time it will take to decide which consistent level you want to use. And we found that for both applications, SIEVE takes less than 0.1 millisecond to finish this labeling, which is quite fast. Okay, for the rest part of the result, please refer to table, refer to all the tables on the figures in our paper. Okay, thanks. So this brings me to the end of my talk. I hope that you enjoy my talk. And in this talk, I hope I convinced you that we built the tool which can automatically select the consistent levels when we build replicated systems. And also try to maximize the part which accept the weak consistent part, and minimize the part really need the strong consistent part. And this work only require little inputs from the programmer, namely the CRDT annotations and also the invariants. Thanks very much. I'm happy to take any questions.
Xiao Zhang from Google. Let's talk. I have a question. Since you have to fetch the weak precondition labeling, how much additional memory overhead is that?
Actually, we didn't measure this memory overhead.
Okay.
The main focus is for this latency stuff. Yeah, latency throughput stuff.
Memory is also very costly.
I can come to you later. Yeah. Okay.
Hello, Raul, Imperial College. I was wondering, so, well, congrats for your work, first of all. Regarding the input from the programming point of view, yep. So you show this strategy with last write wins. Which other choices do you have? And do you have a way of suggesting which might be the good consistency levels for each case, or that's something that is up to the programmer?
So you mean how to select the CRDT tags, right? The CRDT
in
types.
How many choices do I have from a developer point of view? Okay. What are the choices I have to choose the consistency?
Okay. So in our paper, we have the table actually summarized all the CRDT types we support. Okay. So basically, it's covered a large fraction of the related work. So actually, the CRDT part is not the major contribution for our work, yeah, because it's already proposed by a lot of people in different way. So we just sum them up and just.
So the annotations will then choose one out of those set of CRDTs, right?
Yes, exactly. Okay. So that part we require the programmer to think a little bit, because I mean, for example, like the last write win, and also like apply delta, these two strategy. Both of them can ensure state convergence, but they have totally different semantics. So then this require require us to ask the programmer to do that. Yeah.
Thanks. Great, thanks.
Yeah.